Assalamualaikum. My name is Nur Iftikhar Alam Mahir. So, according to my course Electromagnetic Fields and Wave, I am going to design antenna for a LoRa or a long range application. So, for such application, I have choose Yagi Uda antenna working at 915 megahertz. So the common design for Yagi antenna is a reflector dipole and directors. So first of all, we are going to design a reflector keeps it to the y direction, outer radius will be radius, x center will be reflector d into lambda, reflector d into lambda, y minimum will be reflector lambda into 0.5. Copy this, paste this, and now we will give a minus front of the second. Okay, first of all radius will be 1, reflector D minus 0.2, lambda 310, reflector L 2.52. Let's see. Yes, so our reflector design is done. Okay, then we will go toward our dipoles. Sorry. So dipole will be positive. First of all, we will design for a positive dipole. Radius y minimum will be y minimum will be gap into 0.5. Sorry, y maximum will be dipole lambda into 0, sorry, into 0.5. Okay, let's give a gap of 2, dipole L of 0.4. It's slightly smaller than the reflector. Okay, then we will go through our second dipole, giving this a name of dipole negative, and then orientation to y, radius y minimum will be minus dipole into lambda into 0.5. This will be minus gap into 0.5. Let's preview this. Okay, is there a gap for impedances? Okay, then our reflector and dipole is done. Then we'll go to the detectors. D1. give the director of 0.2. Directorial will be smaller than the full dipole, 0.46. Okay. Our second director, 22 radius, slightly higher than our first director. Okay, then our third director, 300 radius. Okay, our fourth and last director, 0.8. Okay, our 4 directors have been designed, almost done. Then we are going to put a port of 50 ohm here. Going to the discrete port, choosing here to here. Okay, so P1 and P2 will be here. Apply. We don't need the second impedance. Okay, apply it. So our design is complete. Then we just need to put a boom now. We are going to design a boom for this design. So let's go to the modeling and design a boom and keep y minimum to minus 200, minimum to 300, x max to 300, y minimum to minus 10, y maximum to plus 10 to minus 10, y max to plus 10. And component, choose the component, new material choosing will be aluminium color, choose the dark color. Okay, so we're going to put all the dipoles. Okay, so let's check our mesh view so that we last keep the frequency first of all. 0.8 our minimum frequency and our maximum frequency will be 1.0 gigahertz. Okay, field monitor will be H field applied, far field applied, magnetic field applied, filters applied. Okay, so go to the mesh view. Yes, we haven't exceeds 1,000, so our simulation will run properly. Close. Now I'm going to close the mesh view. Just going to run now. So let's go to home and start the simulation. Okay. Yes, the project runs successfully. So first of all, we are going to the 1D result and 4th parameter. Let's describe it shortly. So while I have told that we have taken a large frequency, it is giving a 0.96 or 0.5 at very lower loss, minus 16 dB to minus 20 dB. It's showing is minus 20 dB. So then we are going to our far field monitoring value. Let's see our far field cuts. Yep, our far field is good. Let's give it to the structure. And linear, give to the linear scaling, so we can see what direction it is going through. Yes, it is going a good directional, very lower loss directionability. We going to the realized gain, so we can see what gain it is actually working on. Yep. So okay. So see, we are getting total efficiency of 0.98, almost very good efficiency. Our design simulation is successful, our design is successful. As we give more detectors, I think the dBi will increase more, but 4 detector is more enough. And gain is 12.73. our required gain is to 10 to 15, and our required gain is also achieved. So if we go through the 1D result, we see it is going to the 0 point directionality and detector through the 0.0 through the 0 degrees. Then we'll go, if we go through the 2D view, approximately same, and we have seen we noted as 1.2 gain at 12.73. Okay, then we will see the port signal. So the port direction will be coming through towards the gain up front. It's a good directionality as our requirement, and BSW were so about maybe 90% of our frequency is transmitted and 10% reflected. So it is a good design. 90% efficiency to 90 to 90%, 90 or more, even 90%, above 90% is a good design. And the rest of the graphs, there is a many graph like our efficiency, discrete port energy, power, input impedance, reference impedance, many more. So I am going to describe all the tables, all the graphs in my project report. So here is the gain, realized gain. We're going through the part hours gain, total direction, and that's all my design. That's all. Hope I have designed it successfully.